So today my talk is evaluating the epistemic success of causal investigative strategy in neurophysiology. Give me a sec. Right. So the offset of my talk today is to use a case study from neurophysiology to point out various puzzles in the related causal investigative strategy. And the puzzles are about leaving out relevant causal factors and showing little concern to address them. I'm going to adopt some existing philosophical tools and demonstrate how to evaluate the epistemic success of the relevant causal investigative strategy in the case study. And its philosophical significance is this. I aim to provide a way to evaluate the epistemic success of the practicing neurophysiology while justifying why it is epistemically acceptable to leave out relevant causal factors. So the outline for the talk today consists in 3 parts. In session 1, I'm going to present the detail of the case study by organizing them into 5 components and point out the relevant puzzles. The second section, I'm going to review some existing philosophical tools for evaluating the epistemic success of investigative strategy in biological sciences. The third session, I'm going to use the proposed toolbox to demonstrate how to evaluate the epistemic success of causal investigative strategy in the case study. So let's start with section 1. The option in section 1, I'm going to show you that neurophysiologists leave out some relevant causal factors and show little concern about addressing this aspect of their causal investigative strategy, the practice. And the case study is based on a team of neurophysiologists led by Carl Peterson in Switzerland. For now, I'm going to refer to them as the Peterson team. So let's start with the component 1. It's about their causal question about the target phenomenon. So the Peterson team used rodents to study how tactile information signal from whisker to cortex. And the specific brain area they focus is somatosensory cortex, which indicated by the blue area. And more specifically, they focus on specific type of neuron between these 2 layers, layer 2 and layer 3. So their target phenomenon is electric potential of layer 2 and 3 pyramidal neurons in the targeted brain area. And their causal question is what drives the electric potential of this type of neuron in the target brain area. So to summarize, the component 1 is this specific causal question that fits the phenomenon to be investigated. And it is like what drives the electric potential of this neuron. Component 2 concerns the primary causal investigative strategy for neurophysiology. Most of neurophysiology, they work on this causal assumption, which assume that neural signal or transfer information by causing changes in electric potential in other neurons. So just give you a little bit background that electric potential of the neuron is the differences in charge between the intracellular and extracellular side of the membrane. And so for neurophysiologists, their primary target for their causal investigative strategy is changes in the electric potential. And their primary goal is to produce some neurophysiological understanding of how and what neurons cause the electric potential of other neurons. So here I want to make an observation that their primary causal investigative strategies is actually designed to neglect other non-electrical properties of neurons, for example, chemical or genetic properties. And here, there's a puzzle I want to raise is that for the neurophysiological understanding they produce, as a philosopher, how do we evaluate this type of causal understanding produced by neurophysiology compared to the one by molecular neuroscientists, which has been analyzed extensively by other philosophers in neuroscience? So summarize component 2, neurophysiologists' primary causal investigation strategy only enables them to investigate the electrical properties of neuron, not chemical, genetic, or other type of properties. And the possible race here is how to evaluate this type of causal understanding compared to the one by molecular neuroscientists. So let's move on to component 3, which is the actual causal investigative strategy used in the case study. It's called multiple simultaneous in vitro wholesale recording technique. So the Peterson team used this technique because they aim to quantify excitatory synaptic connectivity of the individual neuron of their targeted brain area. So the goal is to quantifying the connectivity. And the recording technique they use is so-called multiple simultaneous in vitro wholesale recording. I'm going to give you a little bit background about the recording technique, and then I will explain how the detail of this set of practice. So in order to record electric signal from neuron, there are 3 ways you can do it. You can insert the electrode inside the cell body, or exactly on the membrane, or outside the cell body. And each way has its strength and weakness. The Peterson team used this one, like insert exactly on the membrane. And the strength of this way of recording is that you get very precise electrical signal, like precise just from this neuron. And on top of that, they are able to apply the skill that after you insert the electrode into exactly on the membrane, you actually create a small hole there, which will cause the leaking of electric signal. So after they insert exactly on the membrane, creating a small hole, they are able to seal the hole. So then it prevent the electric signal from leaking, and that increase the quality of their signal and the data as well. So and then of course they have way to fix rodents' head, so the head movement will not. They can fix the head, then they can prevent the artificial signal. So this is the set of the recording technique they use, and they are famous for applying this set of technique in the field. And as a result, they can get a high quality, no noise, precise electrical signals about neurons. And what they do is they apply this recording technique to simultaneously record 6 neurons on one brain slice. So here you see that you have 6 electrodes recording 6 neurons. And the recording technique is that first they inject, for example, if they inject the current into the neuron 1 to drive action potential in this neuron, and they're going to see if they pick up any positive electrical change in the other 5 neurons. And if they pick up, then they infer that neuron 1 causally connects with neuron 2. So they recorded many neurons on many slides, on many mice, and tested many possible synaptic connections, and they find 909 excitatory synaptic connections. So from this, you can see that their investigative targets actually what I call the rationality of the excitatory information. I will use D to stand for this phrase. And their causal assumption is that they consider D as like the electrical potential of one neuron causes a positive electric change in the electrical potential of another neuron. And in this specific context, the causal reasoning runs like this. So if the excitatory information flows from neuron 1 to neuron 2, then neuron 1 causally connects with neuron 2. But here, I want to raise the puzzle that there are actually, in one brain side, there are actually many neurons, and they only record 6 neurons. And there are other neurons on the same brain slice, and it's possible that their electrical activity also causally contribute to the electrical potential of the recording neurons. So imagine there's the unrecorded neuron, we call it 7. And when you inject current to neuron 1, drive action potential, in fact, then cause positive change in this unrecorded neuron 7. Then the activity here then caused the positive electrical change in neuron 6 and the neuron 2. But because this one is unrecorded, so by all the electro here, you inject current to neuron 1, and you see you pick a signal here, then they infer 1 cause 2, or 1 closely connects with 2. But the Peterson team's reasoning pattern in this context seems to ignore this possibility. And why is that? And can they justify that? Is their causal reasoning defective because they ignore this possibility? Some philosophers analyzing causal reasoning, they think it's very important to control or make sure that you can demonstrate that there's no like a hidden cause here, and it's actually the cause of neuron 2 or neuron 6. So by some standard of proposed by philosophers, this is actually a defective causal reasoning. And so it's puzzling about why they ignore this. So summary of component 3. A specific implementation of the primary causal investigative strategy is this simultaneous eventual wholesale recording. And as I point out that they're ignoring some possibility, and it's actually a relevant electrical causal factor in their reasoning, and how can they justify that? Component 4 is about the network modeling technique. So after they collect all the recording data, they're applying this network modeling technique to visualize neurons they record. And so the visualization is involving, for example, reconstructing the neural structure of each neuron and creating this graph model of how neurons in different layers causally connect with each other. And so they do this kind of visualization for each cell experiment that they perform in their recording technique. So something like this, they just visualize every set. And by doing so, by having this visual diagram to look at and to think about it, they spot a pattern that neurons at the layer 4 usually provide strong output to other neurons at the other layers, but they receive little input from neurons at the other layers. And so this graph is, this diagram is that they averaged across many experiments, and they show that for many different neurons at a different layer, they receive output from L4 a lot, but L4 receives little input from other layers. So by doing this visualization through network modeling technique, they gain an insight that neurons in the layer 4 provide strong effectory output to the neurons at the other layers, but they receive little input from other layers. And this insight enables them to formulate a causal hypothesis, that is to produce a causal claim that the excitatory output from layer 4 neurons makes a dominant contribution to drive the flow of excitatory information further through the targeted brain area. So I want to make an observation that visualization here seems to play a positive epistemic role in generating a causal hypothesis about the target phenomenon. But the question is that if this is the case, as a philosopher, how do we make sense this positive epistemic role played by visualization? Summary of component 4. This is the use of network modeling technique to generate a causal hypothesis. And a question here is that how do we make sense of this use of visualization? So let's move on to the last component, which is the simulation modeling technique. So they use the whole experimental data set to construct and simulate actual and non-actual network models of the target brain circuit. And then run the same computation over these new networks in order to infer what a difference maker is, in order to generate evidence to support their causal hypothesis. So this is the table of the recording data, and they then construct 3 networks and simulate them. The first network they term experimental network, which is the exactly based on the recording data. The second one is Ming network. What they do is that while the network mostly based on the recorded data, but tweak one thing is that they set the firing amplitude of each synaptic connection to some specific Ming value. What this means is that you then, in this Ming network, you don't have some neuron providing strong excitatory output to other neurons. All the connection, all the output from some neurons set to some relative, some Ming value. There's no strong excitatory output in this network. By contrast, this big UEPSP, this stands for the measurement that stands for the positive change in the network. And it's big one because what they do is they remove the small output and keep the big output. And so all the synaptic connections have UEPSP lower than this unit. They remove it, which means they actually remove more than half of the synaptic connection in their original recording data. And so this rare large amplitude of UEPSP is actually the characteristic of the excitatory output of their 4 neurons. And so in the actual network, they do observe that their 4 neurons usually send strong output to other neurons in other layers. So check, it has this characteristic. And so is the third network, the BUEPSP, has this characteristic as well. But Ming network doesn't have this characteristic. That's why they designed the simulation experiment this way. They want to figure out whether this one is actually the difference maker. The procedure is that they use the same computational algorithm to compute the network. They try to figure out the required minimum number of synchronously active neurons that drive a further electrical potential in the network. So the result is that for the actual network or experimental network, they found that you only need roughly 30 layers for neurons. For the Ming network, you actually need double the number. You need 64. And for the big UEPSP, you need roughly the same, 31, as the experimental network. So based on this result, they conclude that this sets of evidence actually support their causal hypothesis that this layer 4 neuron provides strong excitatory output to other neurons is a dominant contribution to drive the flow of excitatory information through the targeted brain area. So here I want to make observation that for them to successfully build a network model for simulation, they don't use any mechanics detail other than those electrical properties, like data they get from recording sets of experiments. So many concerned with some electrical properties, not involving chemical, not involving genetical properties. So the question is, how can they justify ignoring all the relevant mechanism details? And can someone reasonably ask that maybe they need more complete or more detailed mechanism model in order to support their causal claim? So summary of component 5 is that the use of simulation modeling technique to provide evidence for the causal hypothesis and the need to justify the use of it. And the puzzle, And so the puzzle is how they justify ignoring other relevant mechanism detail. So if we put 3 puzzles that I point out in the case study together, you can see that they all involving ignoring or leaving out some relevant causal factor, whether it's electrical or mechanistic. And so there is this fact there that they're leaving out some relevant causal factors. But at the same time, I think it seems to be too hasty to claim that their strategy are not epistemically successful simply because they leave out some relevant causal factors. So here we get the attention is that on the one hand, non-controlling some relevant causal factors seems to indicate epistemic failure on the part of the neurophysiologist. But at the same time, it also seems reasonable to think that their causal investigative strategy have some degree of epistemic success. And so this is the tension I want to address in my paper, and my goal is to show that we can dissolve this tension if we use certain sets of evaluative standard and strategy to evaluate this case study. That brings me to section 2 of my talk, which is to review some existing philosophical tools for doing this task. So the upshot from this session is I'm going to show that Craver and Darden's proposed standards actually can be supplemented by Potucini's epistemic standard. And the structure of this section is I'm going to first talk about Craver and Darden's proposal, and I'm indicating that which part is still insufficient and underdeveloped. And I'm going to bring in Potucini's work to show that her work actually can supplement this part, and that make the whole get ready for the toolbox for us to do the job we need to do in the section 3. So section 2.1 is Craver and Darden's proposal. They propose 3 standards for evaluating the success of mechanistic schemas: depth, completeness, and correctness. So let's start with the first one. This one concerns whether causal representation, whether it requires that you not only superficially re-describe the phenomenon, but reveal how internal structure of the mechanism produces, underlies, or maintains the phenomenon. The second one is completeness. They require that causal representation has to show how each stage of the mechanism allows, prevents, or produces the next stage without significant gaps from beginning to end. But they emphasize that what counts as significant gaps has to be evaluated with respect to various contextual factors. For example, what scientists' investigative goals are, what their related pragmatic concerns are, and so on. So if you read this part, take this part seriously, you know that actually they are not after this very ideal standard of completeness. What they're really after is this acceptable degree of completeness, if this is using their term, and which means the required degree of completeness reasonably matches the various relevant contextual factors at hand. And since it involves a lot of contextual factors, they actually very instructively give 3 strategies you can use to evaluate what they call acceptable degree of completeness. The first strategy is to ask scientists how each stage works in order to see if they can provide sufficient information. The second strategy is to ask scientists what would happen if parts of the mechanism were to work differently. So it's kind of involving some counterfactual reasoning. The third strategy is to see if the scientists have the ability to build an artificial mechanism by using the relevant mechanism schema as a blueprint, or the relevant causal representation as a blueprint. The third standard they propose is correctness. It requires that causal representation must accurately describe the mechanism for the phenomenon. And the adequacy requirement they use is involving some kind of mapping relation between the descriptive element in one's causal representation and to the entity, activity, organization feature of the target system or mechanism. But similarly, as in the case of completeness, what they actually after is also the acceptable degree of correctness. So I want to bring your attention to the following quote. So Craver and Darden writes, I quote, "As with completeness, correctness should be understood as a matter of degree. the acceptable degree of correctness varies from one project to another and one scientist to another. More importantly, however, many, if not all, mechanism schemas indulge in a certain amount of idealization about the mechanism involved. Idealization is the deliberate falsity of the mechanism schema. One might understand the hyperpolarization of rod cells in the eye in terms of a model that treats the neuron like an electrical circuit that obeys Ohm's law, knowing full well that neurons technically do not obey Ohm's law. As we noted above, criteria of the correctness often must be weighted against other virtues in choice of mechanisms. Here, it is more appropriate to talk about a schema being correct enough rather than correct full stop. So what this quotation shows is that they really after a acceptable degree of correctness. And more importantly, this widespread use of the idealization they acknowledge partly motivate them to use this notion. But unlike the case of completeness, they do not give any specific evaluation strategy for us to evaluate, okay, in this case, what counts as an acceptable degree of correctness. Especially think about this question is that when Craver and Darden's accuracy requirement, which is that mapping relation, is achieved by making a false assumption about the target, how do we evaluate the relevant degree of correctness? So we need to account for this connection between idealization, saying some false about the system, and the acceptable degree of correctness. So summary of session 2.1 is that you see these three standards and they give you a detailed strategy, but in this part, there's still some insufficiency or underdevelopment. And here's where I think Potocini's work is relevant and can supplement their work. But I want to first note that, of course, there's a difference between them. Craver and Darden focus a lot on analyzing mechanism schema. Potocini mainly focus on analyzing causal pattern. But for the purpose of my paper here, it's about how we understand causal investigative strategy, how to evaluate the causal representation. And in fact, Craver and Darden and Potocini, they share the following view. They both agree to use we use a space-time relationship. That's the kind of relationship allow for further manipulation and control, and basically they all endorse Woodward's interventionist account causation. And I think that we use this type of relationship to epistemically characterize and justify biological scientists' causal claim, causal representation, or their causal practice. So that's focused on how Potocini's analysis of idealization. She defends the view that idealizations play a positive representation role in science. So in the current model-based literature, there's a consensus that idealized model or like idealized representation, idealized model can represent. But philosophers disagree about the role idealization play in the idealized model. Some philosophers think that idealization mainly play the role of eliminating irrelevant features from a model. And Potocini actually holds a stronger view. She thinks that idealized models do represent, partly in virtue of representing a system as if it possessed one or more features that it does not. So put in another word, she thinks that idealization adds content to the relevant representation. And the way idealization adds content to the representation is by saying something false about the system, by saying the system has some properties, features, but in fact the system does not have. And she called this role representation as is. And the important thing is that if you think idealization's role is just eliminating irrelevant feature from the model, it sounds so awfully like abstraction. But in Potocini's account, because she assigned this specific representation role to idealization, she's actually, according to her account, she's actually able to make a clear distinction between idealization and abstraction. So idealization helps represent a system as if it has some features it does not have, whereas abstraction helps omit some feature of the system in a justifiable way. And this distinction is going to be relevant for what I'm going to do in session 3. So please keep in mind. So now the question is, if idealization can contribute to any acceptable epistemic achievement in science in virtue of playing this role of representation as is, they do so by departing from truth, by saying something false about the target system. So it seems that we need a specific kind of epistemic norm standard in order to make sense of epistemic value of idealization. A simple truth norm cannot serve this purpose. And Potocini actually does exactly like she proposed a epistemic standard called epistemic acceptability to do this job. So according to her, a posit is epistemically acceptable when its diversion from truth is insignificant, taking into account A, the posit's role in representation. It could be idealization, it could be abstraction, it could be a claim, asserting something, it can be whatever. And B, the epistemic purpose to which that representation is put, whether that representation is for predicting, for different kinds of epistemic purpose. So I'm going to use the example Potocini used in her book to illustrate this standard more concretely. So consider the posit that electrons follow classical orbits. And there's one case where if you use this posit, it's actually epistemic acceptable. But there's another case, you use the same posit, but it's not epistemically acceptable. So in the first case, it's epistemic acceptable when this posit is used as an idealization, deliberately saying something false about the system, because electrons do not really follow classic orbit. It's false in quantum physics. And B, this posit uses idealization in an account that explains the phenomenon related to atomic photoabsorption. And there's some case detail I need to really go into in order to make sense, but I don't really have time to diverge on that, to dwell on that. So I will just give you a very general statement here. But in another case, the same posit, electrons follow classical orbit, is not epistemic acceptable as a claim to asserting something about the system, and as a claim of classical mechanics taken as a theory. And for there's a clear evidence that electrons are not discrete entity following such orbits. So her proposed norm standard allows us to evaluate under what condition a posit, especially, for example, idealization, is epistemically acceptable for its epistemic value, even though it departs from truth. So what I propose is to use Potocini's notion of epistemically acceptable posit to replace Craver and Darden's notion of the acceptable degree of correctness. And it has two advantages. One is that it really clarifies how idealization can be evaluated with respect to its epistemic value. We don't rely on simple truth known. We use epistemic acceptability. And it provides a better understanding of the Craver and Darden's notion of acceptable degree of correctness, especially in view of the idealization. So the sum of the session 2 is that now we have 3 standards and some related strategy we can use. One is depth, second one is acceptable degree of completeness, and the third one is the acceptable degree of correctness, or epistemically acceptable posits. So remember, this is the tension I pointed out earlier that I want to dissolve in the section 3. On the one hand, you have non-controlling some relevant causal factors seem to indicate epistemic failure, and on the other hand, it seems reasonable to think that their work has some degree of epistemic success. So session 3, I'm going to apply the tools to demonstrate how we evaluate the case study. So first thing we need to do is that, of course, now we acknowledge that it's important to get the context right in order to know what are the relevant contextual factors we need to consider. So the first step is to fix the evaluative context. In my case study, what is really the main aim is to provide a neurophysiological understanding of what drives electrical potential. So when we evaluate whether a specific policy serves a specific goal or not, our evaluative activities as a philosopher have to be conducted within this context. It's about providing neurophysiological understanding. The second step is to fix the most relevant representational products for evaluating the epistemic success. One is the table of quantified measure as is the outcome or product of their recording experiment, which I remind you is this table. And the other one is a set of computational model they build to run the simulation experiment. So the third step is we fix the relevant standards and strategy we're going to use. And that's basically just plug in what I talked about in the session 2. So let's start with the standard of epistemic acceptability. In order to apply this standard, then we need to identify the relevant posits in a case study. So there are two. One is in both component 2 and 5. The other is in component 3. So we analyze this one first. The posit in component 2 and 5 is neuron signal or transfer information to each other through electrical activity. So that's just applying these 2 questions we need to ask. What is the posit's role in the representation? I want to claim that the role here is actually abstraction, omitting features and can be justified. So in this posit, the relevant genetic and chemical causal factor, in fact, at the end, will channel their causal inference through the difference they make in electrical properties. And so the relevant representational product, in an indirect sense, still include causal inference from the genetic and the chemical factors, but they're not the detail regarding how exactly they do that, because how exactly they do that is fall outside the focus of what neurophysiology aims to achieve by generating neurophysiological understanding. So that's the role of abstraction, and that's the epistemic purpose to which that representation is put. And as I mentioned before, it's for producing a neurophysiological understanding of target phenomena, which means the targeted causal pattern is at a scale of electrical properties, not a chemical, not a genetic property, but electrical property. Now let's consider the posit component 3 is that if excitatory information flows from the recording neuron A to the recording neuron B, then A causes B. But as I mentioned earlier, it's likely the case that there are other non-recording neurons on the same recording brain side mediate between A and B, as this case shows. So when this is actually the case, strictly speaking, this posit is false. The posit asserts that A causes B when it is not the case that A causes B, at least not in a direct sense. But their actual recording practice, however, does not involve controlling the condition to make this posit always assert something true about the brain slices. Remember, they record 300-something brain slices, and in some cases, this posit might asserting something true about the target brain circuit, but a neural circuit, but in some cases, maybe they say something false about it. This means that their causal investigative strategy in component 3 is epistemically unacceptable and hence unaccessible. So again, we apply that standard to evaluate. Let's assume that the posit is used as an idealization and examine whether or not this idealization serves the purpose well. So the idea here is that, well, I focus on the cases where they get wrong, because that's what really matters. If they get right, they get right. But the cases where they get wrong, in this case, this posit plays idealization role. Okay, now the next question is what the epistemic purpose the use of this idealization aim to achieve. In component 3, the aim is to quantify the underlying excitatory synaptic connectivity of the target neuron. It's not about providing a direct causal answer or other things. It's about quantifying connectivity. And there are two important reasons for them to idealize. Otherwise, the experiments cannot be carried out in any further stage, because without any quantified measures of neural connection as their starting point, the subsequent modeling tool, for example, network modeling and simulation modeling, have no use for neurophysiology at all, because these two sets of technique all require you have quantitative measures of neural connection, so then you can start doing modeling work. And so this is a very important first step, that you just need to get some quantitative measures to begin with. Otherwise, even though they know how to use the tool, but they don't have data to start with. Another big reason for them to idealize is the limitation of their impressive recording technique. As I mentioned earlier, the recording technique is very impressive, and in fact, using that recording technique and able to record 6 neurons on the same brain size already very demanding on the part of neurophysiologists. So in principle, it's physically possible to record all the neurons on the same brain slice, and so I can really figure out exactly when there's a hidden causal factor or not. But it's technologically impractical or even impossible for neurophysiologists. So this is two very strong reasons for them to use this idealization. But so the job is to get some good enough quantitative measure to start with, and this idealization actually serves its purpose well, even though some of the causal connections are falsely represented. So that's the part about the first standard of epistemic acceptability. Now let's move on to the other two standards, and we'll start with the depth. So let's examine the causal representation. That's that table of the recording data, and we're going to see whether it superficially redescribes the phenomenon. So this table of recording data or quantitative measure enable neurophysiologists to employ the network modeling technique to visualize and investigate the internal structure of the target neuron. As I show you that they do the reconstruction of the neural structure and then generate graph model of their causal connection. And as a result, they actually gain insight about the layer 4 neurons and generate a causal hypothesis. So in this case, this table of quantitative measures do not just redescribe the phenomenon. So now this slide is to remind you that in the case of completeness, Quaver and Darden actually propose 3 strategies we can use. You can ask scientists how each stage works, ask them like what would happen if parts of the mechanism were to work differently, and you can ask them whether you can see whether they can build an artificial mechanism based on their causal representation. So their ability to visualize recorded data, in fact, implies their ability to build artificial network based on the table of quantified measures. Their ability to answer how excited information flow among the 6 neurons that record simultaneously. So in this case, that's also satisfied the acceptable degree of completeness with respect to the epistemic purpose of quantifying the underlying connectivity. Okay, now move on to the the second representation, that is the set of computational network for doing simulation. And about the first standard, because it's based on the component 3, which is that table of quantified measure. If quantified measure satisfied, naturally component 5 satisfied. So we only need to deal with the completeness part. So I think the computational model also satisfies the standard of acceptable degree of completeness with respect to providing evidence to support a causal hypothesis. The computational model they construct in the simulation experiment is demonstrate the ability to build artificial network again, and also the involving actual and non-actual, because they can tweak some feature in the artificial network. And they are able to answer the type of question about what would happen if part of the network were to work differently. That's demonstrated by the Ming network and the big UEPSP network. And they certainly have the ability to answer how each stage works with respect to the neurophysiological understanding and to produce. Okay, so here's the conclusion I want to draw now is that by applying the evaluative standards of depth and acceptable degree of completeness and epistemic acceptability, the tension identified in the case study is dissolved. The causal investigative strategy and the causal representation in the case study are epistemically successful by satisfying the standards of these 3 standards, despite the fact that they leave out relevant causal factors. Thank you.